Welcome to the array storage part of the tutorial. In this part, we cover database and file-based approaches to array storage as well as relevant compression techniques. We also mention several attractive and promising R&D opportunities. Chunking partitions an array into a set of I/O units called chunks. Chunking is an approach to substantially accelerate I/O. What is the best chunk shape? Consider an example. Given an array of 12 by 12 cells, the task is pretty simple. We need to read a 6 by 2 subarray from the given array. Without chunking, we need 6 I/O requests to complete the operation. We can chunk the array, for example, in this way. However, this situation gets worse, as now we need to read 50% of all data to retrieve the slice, despite that we issue only 2 I/O requests. A better chunking would be similar to the case C. We still do only 2 I/O requests compared to 6 requests of case A. But we read almost exactly the array portion we need. This is only one example. The trick is that the best chunk shape depends on the workload, which you do not generally know a priori. Moreover, the chunk workload can change dramatically. Chunk shape is a crucial performance parameter. For different chunk shapes, the performance of, for example, ChronosDB differs by orders of magnitude. In addition, there is no best chunking scheme for all workloads. As you can see, the extraction of a time series runs the fastest on chunk shape D. Hence, an array DBMS must be able to quickly alter chunk shape. Suppose an array DBMS workload changed. Now, you need to chunk your array to a shape that is better suits the workload. ChronosDB is up to 1000 times faster than ChronosDB for the chunking operation. Please choose the right database for your tasks. Almost all array DBMSs or array storage systems utilize chunking. ChronosDB keeps data in diverse file formats. ChronosDB and ChronosDB use regular chunking. TileDB operates on data tiles that have the same number of non-empty cells to facilitate load balancing. Rasterman stores array tiles in blobs and provides 4 tiling strategies. These are regular, used by most systems, irregular, partially aligned, and totally non-aligned. The documentation gives some hints on what strategy to use, but it's up to users to pick up a strategy and its parameters for better performance. Array Store investigated tiling techniques for clustering, slicing, and other workloads. They also use two-level tiling strategies, both regular and irregular. They conclude that a two-level regular tiling works best for most workloads they tested. TileDB targets multiple cell-wise random writes in batches to different array regions and fast reads of the resulting array. TileDB writes data in fragments, time-stamped snapshots of batch updates to an array. An unempty cell from a newer fragment overrides an unempty cell from an older fragment. The core idea behind TileDB is as follows. A fragment can be represented as a set of 1D fragments. TileDB sorts the segments by timestamps, intersects them, and reads only the newest updates. For example, 2 latest segments overlap as they updated the same subregion. TileDB will discard some values from the second fragment as they are outdated. Nowadays, chunk shapes are mostly hand-tuned experimentally by ArrayDBMS users. Research literature proposes some automatic chunking strategies, but apparently they didn't find their way to ArrayDBMSs. We need novel, more general heuristics for automatic selection of proper chunk shapes, especially in runtime and especially for interim arrays, as users don't control their parameters. What about file-based approaches? ArrayDBMSs serve diverse scientific communities that collected and processed array data for decades before ArrayDBMSs appeared. Terabytes of array data collected and generated daily. Hence, arrays natively come in diverse file formats including netcdf, HDF, GeoTIFF, and hundreds of other file formats. Novel and database storage approaches require time-consuming data import phase. However, arrays natively come in diverse file formats. Moreover, arrays are also shared in established file formats. In addition, update workloads are currently rare in many application domains, as scientists almost never delete or update original data. A closer look at popular file formats reveal that they are like small databases. For example, GeoTIFF represents an effort by over 160 different parties. It has a lot of capabilities, including overviews, that is, array instantiations for multiple zoom levels, tiling, varying number of bits per cell, support for large and sparse files, and so on. So the natural question arises, why not use these powerful storage containers directly as a storage layer of an ArrayDBMS? That's exactly what ChronosDB is doing. Its storage layer is based on established standardized file formats. Files are distributed among cluster nodes and processed in parallel. The ChronosDB data models abstracts from the files and treats all related files as a single array. Unlike other DBMSs, ChronosDB omits the time-consuming import phase. ChronosDB immediately gets powerful storage capabilities that include storing diverse data types, efficient missing values support, and numerous compression techniques out of the box. Moreover, ChronosDB arrays are readily accessible to any other software as a set of ordinary files. For example, geographic information systems are Python and many other software that just can read such files. Nowadays, established file formats like HDF5 are being adapted for storing sparse arrays. The key challenge here is not to introduce breaking changes to an existing API. Most such work is just commencing. In addition, recall that there are hundreds of array formats and you can always design your own. For example, for specific workloads or operations. Array compression falls into three categories: general purpose, used not only for arrays, and developed specifically for scientific arrays and ArrayDBMSs. All three types are used by ArrayDBMSs. The first category is relatively well known. The third category will be covered during the array indexing part of this tutorial. So now let's focus on the second category. Experiments on real-world data reveal that general-purpose compression does save quite noticeably the storage space. For example, Deflate can save up to 30% of storage space for Landsat 8 satellite data. However, there is almost no difference in comparison ratios between the slowest and fastest settings. However, RateDBMS performance on original and compressed data is almost the same, be it TileDB or ChronosDB. So we do not save space and read less from storage, but we need additional CPU time to decompress the data. Hence, researchers developed compression techniques specifically for scientific data. These data constitute a large portion of RateDBMS workloads. One of such techniques is precision-preserving compression. It eliminates false precision without compromising scientific integrity of data, and then its goal to facilitate and further reduction of data volumes. Consider a real-world example, air temperature from the 20th century reanalysis project. If we look at the metadata, we will immediately notice that the values are stored as floats, that is 4 bytes per value. However, the precision is only up to 2 digits after the floating point. The table on the right shows a small sample of the values. Let's apply BitGrooming to this temperature data set. The values change slightly, but they are still equivalent when printed with 2 digits after the comma. Let's take the top left value and look at its IEEE representation. The difference between the original and produced values is acceptable, and we can reliably say that they are identical. However, BitGrooming created a sequence of 5 0 bits at the end, amenable for better compression. PPC itself doesn't compress data. It creates longer strings of identical bits that are amenable for better compression. A typical pattern is to feed the PPC output to lossless compression technique. For scientific arrays, this yields much higher compression ratios at relatively the same speed compared to general-purpose compression. Please compare Google Snappy and digit rounding so presented on this slide. Interestingly, PPC techniques are fast and relatively simple, so it's very encouraging to do something similar yourself. For example, the key idea of digit rounding is to calculate a quantizer full of zeros to avoid divisions for each input value. You can find a clear explanation of the formula in the paper. Note that digit rounding was originally proposed for datasets in netcdf4 or HDF5 files. Why compression algorithms for established file formats are important? You could say that many other techniques exist. Sure, but the main advantage of file-based techniques is interoperability. They're readily available for numerous software that can operate on these files, for example, ChronosDB or RateDBMS. From the software engineering perspective, your investments into file-based techniques are minimized as they are already implemented and thoroughly tested. Finally, I'd like to showcase one of the most promising opportunities where one can immediately obtain results. There is a lot of work on NVM and relational DBMSs, but NVM approaches proposed specifically for array DBMSs are lacking. Just common research. Most of your ideas specifically for this yarn area, I mean array DBMSs, will be novel and highly demanded.